Hi everyone, and welcome to a new video about the new series of noise analysis in electric circuits, and this will be our example number 1. And in this example we will look at a very simple resistive circuit, so that will be a passive circuit, and then we will look how we can determine the noise of the input and noise of the output, and also the signal to noise ratio, and also different aspects. So let's look at our example. Of course, we will look at our calculations step by step and then verify these calculations and simulations in SPICE. So let's look at our example. This is the circuit we have given, very simple circuit. We have the R1 and R2, two resistors, and it has a voltage source VN applied, and we will measure the output across the resistor R2. So we have 1 kilo for the R1 and 3 kilos for the R2. And the VN is just an AC voltage source. So what we want is, of course, there are several questions. We have calculation of the output noise voltage spectral density, which is given by E sub n out. We also want to have the input noise voltage spectral density, which is then given by E sub n in. We also want a total RMS output noise voltage, which is then given by the capital E sub n out for the following signal bandwidths. That is 1 kilo hertz, 10 kilohertz, we have 100 kilohertz, and then etc. for 1 megahertz, 100 megahertz, etc. So that will be then also calculated for several different frequency bands. And finally we will look at the signal to noise ratio, which is then short as an R. That will be also discussed. So how do we start? Let's give a brief introduction about the noise, because noise is a very broad subject, so I'm not going to dive into a lot of details, so I will give you just what you need for this example. Okay, solutions step by step. Of course, the procedure what I will use for this example is the following. I will disable the independent sources. That can be a current source, voltage source, doesn't matter what you have here, that will be disabled. In this case, since this is a voltage source, it will be a short in our analysis. So that means input voltage is a short. Now, we also use noise voltage sources or current sources, of course, but in this case I'm just using the noise voltage sources associated with each resistor. So each resistor will have its own noise voltage source. And that is then given by these elements, so values. So we have the E n sub n of R1, that is actually the noise spectral density, noise voltage spectral density specified by R1, and noise spectral density of the R2. So if you now use these two elements in this circuit and then disable, of course, the input voltage, then you will have this model. The R1 is now here, and that is now a noiseless resistor, and this is then the associated noise voltage spectral density. That's given by this. And now the R2 also, in this case now the R2 is noiseless, so it is a noiseless element, a component, but it has its own noise voltage spectral density in series. This is also a model. You can of course have the R1 in parallel with the noise current spectral density. That can be also done for R2. That is really what you also can work out in a different form. Okay, then of course the procedure is this: first the model, and then we will use superposition. Just activate one source at a time and then look at the response in the output for each of the elements, and then combine them using linear combination. That's what the superposition principle will be. Now let's summarize this very quickly. What is non-thermal noise power? Because the noise power is where we start and then we go to the noise voltage. So noise power spectral density is given in general by this expression, which is then, of course, now you can see that the power is the voltage squared here, and then that's given by 4k TR, and this will be clarified shortly. You can see that the units are V squared per hertz, so we actually have the voltage squared per hertz. So it depends still on the frequency, so it is actually not just a constant value, it is really dependent on the frequency. Now you can of course go from this to determine noise voltage spectral density, and that is given by this expression in general, just square root of that one. You can see that it's just now E, noise voltage spectral density then, sub n, and that is then now the square root of what we have here. And you can see that this is now volts per root hertz. And that's a little bit different unit than what you most of the time use, because you only see the amperes, ohms or volts. But now we have a really strange unit actually, which is then the root hertz. But that will be fine when you see the analysis in more detail shortly. Now, what is actually what we have here? So we have again a KTR. That will be of course a little bit unclear for you, maybe for the first time. The K is just a constant. It's called the Boltzmann's constant. So it is given by it's given as a unit joules per Kelvin, or for short J over K. And then we have the small letter K, which is then the Boltzmann constant, given by this value. Of course, this is just a very approximate value that can be of course made a little bit exact, but this is what we use. So this is 1.38 times 10 to the power minus 23 joules per Kelvin. The T is the absolute temperature given in Kelvin, so not in degrees. And for room temperature, for example, at 27 degrees approximately, for that operation we use the T is 300 Kelvin. So in our calculations we will use this. If you of course want to have it in a very hot area or maybe very cold area, of course you need to change your value of K, or I mean T, for the temperature, absolute temperature. Now the R is the equivalent resistance actually in ohms seen at the node. So for example, if you're interested in this node, of course in this node in the actual circuit, then this node is then looking from this node to the circuit, of course this disabled, maybe it's better to look at this model, then you have the two resistors actually in parallel. Then you have R1 and R2 in parallel, then you need to determine the equivalent or effective resistance or impedance seen at this node. That's actually what you need in this expression. So let's move on, and we'll be clarified more in more detail using numbers. So again, these two figures, so we have the circuit itself and also the model. So let's look at the noise voltage spectral densities for each resistor using the description we have seen shortly. So for resistor R1, we can then rewrite this formula. So we can say the noise voltage spectral density for our resistor R1 is just using this formula, and then I substitute the values. Just 4 times the Boltzmann constant times the absolute temperature, which is the room temperature at the moment, and then the resistor value, which is then 1000 ohm, and then you will have this value, which is then 4.07 nanovolts per root hertz. So that will be your result. That will be then also done for resistor R2 in a similar form. So you have then the noise voltage spectral density for your resistor R2, and then you do the math again in a similar form, but then of course your resistor is 3000 ohms, and you will get 7.05 nanovolts per root hertz. Okay, now I have the two voltage sources, noise voltage sources, actually in spectral densities in my model. Now what do I do next? I use superposition to use these two voltage sources and then make it actually one noise voltage source or noise voltage spectral density. So the for R1, the output noise voltage spectral density, due to this only, that will be of course just activating this and then looking at the value what you get here, just looking at this source. So actually I'm disabling this, that will be a short, and I look at this value, only the input for this noise voltage spectral density due to R1, and then I calculate what the output noise spectral density then will be. So I have then this expression. So the output noise spectral density due to only the R1 noise spectral density will be this. This is just the voltage divider rule. You can see that it's R2 divided by R1 plus R2 times this voltage noise spectral density. So you will have this. And if you now calculate this out, just using this value we have for the noise voltage spectral density for R1, using the ratios of the resistors, I have then the result as follows. And this is then the value for just taking into account the noise voltage spectral density of the R1. That is the output noise voltage spectral density due to R1. In a similar form for R2, you can then say disable this and then look at only this. Then you have the R1 over R1 plus R2 times this, which is actually what you have here. So that's just again voltage divider rule, just using superposition. You do the math, you will get this value and you will have 1.763 nanovolts per root hertz. So we have this and these values as the output contribution for our noise voltage spectral densities that will be combined using superposition. So the total output noise voltage spectral density will be then the square root of the square of these and the square of these one, and then sum them together. So you will have the square of each term plus and then root of these, and you will have the following expression, and that will be approximately 3.525 nanovolts root hertz per root hertz. So that is what you now have for your output noise voltage spectral density. We will use this, of course, and you will already see that this is frequency dependent, and that will be, of course, then used to determine the actual RMS noise voltage at the output. So let's look at the following situation, but let's also look at it in a different form, because there is an alternative calculation for this one. So it's not only using the model where you have the R1 in series with your noise voltage spectral density. I already said that in the beginning. You can also place the R1 in parallel with our noise current source noise current spectral density. That's also possible. It can be also done for R2. It's actually what you prefer, but I will now do that by using Norton equivalent circuit. So I can say transform your circuit in a noise model where you don't use a thevenin, actually series combination of the resistor and the voltage source, noise voltage source spectral density, but use a Norton equivalent, which is then the R1 as a resistor in parallel with the current noise spectral density. So then the required parameter for that one is the equivalent resistance seen at these nodes. I will just call that R equivalent. And I will also need the total input noise current density, which is then given by IN total. Since this will also have its own noise current density, and this will also has its own noise current density, then I will have then again the square root formula to determine the total noise current density. Now let's start with the equivalent resistance, which is just the parallel combination looking at this node. So you disable all the noise current source spectral densities, and then just look at the two resistors. These are all parallel, of course, R1 and R2 are in parallel, and then you will have this calculation that will be then in effective form 750 ohms. Just do the math here for yourself. It's a very straightforward formula. And then the noise current spectral density due to the R1 only is then given by this. Just looking at this one, then transform actually this thevenin form in the Norton form. So you will have then the parallel combination of the R1 with the noise current spectral density. Then that will be the following. You have the E sub n R1, which is already calculated. Over that resistor value, then you will have this value for your noise current spectral density due to R1 only. And a similar form you can do it also for R2, and that's then given by this. Again, you divide by the associated resistor. So this is then the current noise current spectral density due to R2. This is noise current spectral density for R1 and this for R2. Now we will combine these to get the total input noise current density. This is then given by this formula. Again, very straightforward formula using the square of the square root of the squares and then add them together, of course, first. Then you will have this formula, just add them up and you will have the value here. That is approximately very close to actually 4.7 picoamps per root hertz. Now we'll use Ohm's law because we want to have the calculated value for the output noise spectral density in total. That will be just the current times this resistance which you see at this node, which is then 750, which is then the equivalent resistance. So it is just the noise current, total noise current spectral density times the equivalent resistance. Just do the math for yourself here and you will get 3.525 nanovolts per root hertz. And this is exactly the same result using the superposition principle. So it really depends on what you prefer. So you can use the thevenin or the Norton equivalent circuit and then determine the required value at the output or maybe at the input. It really depends on what you prefer. Okay, let's move on and then also look at the input noise voltage spectral density, which is then given by this En sub n. For the total, of course, we will for that use a signal gain from the input node to the output node, and that is then given by the voltage divider rule, because we know that this circuit is used, and for the signal gain, which is actually the gain specifically looking for the signal, that will be what we have at the output divided by what we have at the input, and that is then calculated using the voltage divider rule, which is just R2 over R1 plus R2, 3000 over 4000. Just do the math here and you will get 3 over 4, 0.75. Now, using signal gain and also the total output noise spectral density, we can calculate the total input noise spectral density. So, again, using this model. So, we know E n out, which is a small letter E sub n out, which is then the output noise spectral density, is then the gain times the input noise spectral density in this case. So we have then the gain and we have the input noise spectral density, just actually a very straightforward formula, and then you have the output noise spectral density. Now if you rewrite this a little bit, then you can calculate the input noise spectral density. Just you rewrite this formula. Now you have this already calculated in the previous analysis, and if you now divide it by the gain, then you will have this value. Actually, I really need to use the noise gain and not the signal gain for calculations, but since there is no different or another noise gain in this example, that will be clear when we also discuss the op-amps and transistor noise analysis, then we'll see also that we have a noise gain and also a signal gain that doesn't have to be equal to each other. So in a precise form, I really need to call this a noise gain, but in this case, since there is just a signal gain, I will still call it the signal gain, but it's actually in precise form the noise gain. So getting back to this input noise spectral density, this will be then 4.7, approximately very close to 4.7 nanovolts per root hertz. So now the next one was the total RMS output noise voltage, which is then given by the capital letter E sub n out. Now since we know this, which is then the small letter E sub n out, which is then the total output noise spectral density, I can now calculate the total RMS output noise voltage, which is just given in the RMS voltage, which is independent on the frequency. So for that we integrate the output noise spectral density across the complete noise bandwidth. Again, we don't use the signal bandwidth, but we use the noise bandwidth. So not the signal, but the noise bandwidth specifically. In this passive circuit, we don't have a cutoff frequency or any other frequency limiting part. So that means the following: the signal bandwidth, which is given by SBW, is infinite because there's no frequency limitation anywhere. If we don't have a capacitor or inductor, no frequency dependent component. So that means in this case, specifically in this case, because we have a pure resistive ideal resistor, of course, we have a noise bandwidth which is equal to also infinite, and that means this is also a zero-ordered circuit, so there is no dynamics in it. That means there's noise bandwidth will be equal to the signal bandwidth. So we have the noise bandwidth that will be equal to the signal bandwidth. This is really important because you really need to use the noise bandwidth for your calculation, not the signal bandwidth. That can be give you the wrong results. So the value for the RMS output noise voltage is given by this formula, which is then the RMS output noise voltage is given by the output noise spectral density times the square of that noise bandwidth. So really need to use that noise bandwidth. And in this specific case, it is the noise bandwidth which is then equal to the signal bandwidth. That is just a situation where we have only passive components. So that is just a special case. Now let's also look at it then for different frequencies or different signal frequencies, and in this case also different noise frequencies or noise bandwidth. So the RMS output noise voltages are then for, let's start with 1 kilohertz. What we have then is just substitute in here 1 kilohertz for your formula. You will get very close to 111.5 nanovolts RMS. So you can see that this is independent of frequency, just this value at this frequency band. If you increase your frequency 10 times larger, then you will have this noise voltage in RMS. So it is actually increasing. Now if you increase it even more, so I go to 100 kilohertz, I will have this value, just substitute in here 10 to the power 5 hertz. So you're already at 1.115 microvolts RMS. So you can see that there's an increase here of 10 times. So you increase actually your frequency here from 1 kilohertz to 100 kilohertz 100 times, but the RMS noise voltage at the output is increased now 10 times because there's a square root term here for the noise bandwidth. Now if you move on like this for different frequency, 1 megahertz, 10 megahertz, 100 megahertz, also 1 gigahertz, you'll have these results. And if you now summarize this in a table, you will have this result. So the frequency band, specifically the noise band, 1 kilohertz, 10 kilohertz, etc. So you will increase actually in 1 decade in steps. Then you will see that the total RMS output noise voltage is then also increasing. But you can already see if I go up 10 gigahertz, maybe 100 gigahertz, etc., this will just increase. So there is no limit in this case. So you will have an increasing noise if you increase also your bandwidth. That is of course important, because sometimes we say I won't have an infinite bandwidth, but it's of course also infinite noise. So that is one of the problems when you have no filtering at all. So let's then look at the next analysis, which is then the signal to noise ratio. What is the signal to noise ratio? Which is a very important parameter. Signal to noise ratio, SNR for short, is a measure that compares the desired signal level to the noise level. So what you have is of course your desired signal level, and what you don't want is the noise level, and the comparison between these two is the ratio actually is then the SNR. It's actually similar to common mode rejection ratio, CMRR, but this is then using the volts levels. So SNR is then defined as a ratio of the signal power to the noise power. So it is then expressed in dBs. You can also have it as a scalar value, but most of the time you will see that also in the datasheets as a dB. So a ratio, for example, higher than 1, greater than 0 dB, indicates actually there is more signal than noise, which is of course good. Of course, we want to have a very large value here, such that there is a very nice suppression of, or very nice separation actually between the desired level and the noise level. So for this circuit, the SNR at the output for a specific frequency can be calculated using this expression. So again, this is directly given in dBs, so we have 20 log of 1 over that output RMS noise voltage. So again, the table, we have calculated this for different frequency bands. This is the total RMS output noise voltage given in RMS, of course. And then for a given signal band, or noise bandwidth actually, in this case, bandwidth, the corresponding SNR. So since this is of course, again, let me remind you, the signal bandwidth and a noise bandwidth for this circuit is exactly the same, because this is a passive circuit, so you don't have any frequency limitations or any other issues, because there is no dynamics in the system. So the corresponding SNR at the output will be then for each frequency band as follows. So noise bandwidth for 1 kilohertz, you just do the math using this formula. You will take this value for 1 kilohertz and you do the math here, and you will get 139 dBs. You do that also for 10 kilohertz. Again, just grab this value from the table and then substitute it in here, and you will have 129 dBs. And also for the other one, so 100 kilohertz, 1 megahertz, 10 megahertz, 100 megahertz, and 1 gigahertz. What you see is actually that the SNR is decreasing when the frequency is increasing. So if I increase my frequency 10 times, the SNR is decreased by 10 dBs. So it is just 10 dB lower when I increase my frequency 10 times. So if I increase my frequency now 100 times, my SNR will decrease 20 dB. So it's actually what we see also in this form. So if I now collect these together in a table and also give this value of the SNR, I mean the total RMS output noise voltage, and the SNR next to each other, you can see that if the frequency is increasing, the noise will increase. So you can see it's nanovolts RMS, but now it goes to microvolts, so it is increasing. But SNR will decrease. It is actually very straightforward, because if I have a more noise voltage, the SNR will of course decrease. So you will have a decrease from 139 dBs all the way to 79 dB if you go from 1 kilohertz to 1 gigahertz. That is what you see in this table. So in conclusion, the larger the frequency band, the larger the noise voltage, and also the smaller the SNR, which is straightforward of course. And that is what you also see here in the table. So let's also look at the simulation results. I already prepared the plots for you. So I first start with the output noise voltage spectral density. This is given here. What you see is that the output noise voltage spectral density is a constant value here. So it is for these frequencies, several frequencies from 1 millihertz to 1 gigahertz. And this is the output noise spectral density. You can see it is 3.5 to 6 nanovolts root hertz. And we had calculated very close to that value actually, 3.5 to 5 nanovolts per root hertz. So it's actually very close. That's actually very, very nice. And this was a circuit where we have the analysis. So what you see is the noise output noise voltage spectral density is a constant for all frequencies. So we have this actually for all values of the frequencies. That doesn't have to be the case. If you look at, for example, an op-amp, that will change and you will have different bands and different regions where you see the output noise spectral density is changing. Okay, that's for this. Input noise voltage spectral density, that's what we have here. So I just look at the input. You can also see that input noise spectral density here at the y-axis. For the vertical axis, and for the x-axis, horizontal axis, you can also see again the frequencies from 1 millihertz actually to 1 gigahertz. And again, this is the value 4.701 nanovolts per root hertz, and we had calculated this value 4.700 nanovolts per root hertz, which is very close to that one. So that's also very nice. So the total RMS output noise voltage. This is the result. This is the total noise, which is given of course in RMS, and this is the frequency and the horizontal axis. What you see actually, we have for several frequencies, I already made some labels, the total output RMS noise voltage. Now, if I look at the formula we have used of course here, and the output noise spectral density was given by this value, and if you now use this here, that green value here, and then do the square root of that frequency band, you will have then this table. We have already discussed this. But let's look at, for example, the 10 kilohertz here. 10 kilohertz was 352.5 nanovolts RMS. That's very close to this one, which is actually 10 kilohertz. If I look, for example, at 1 megahertz, that is then, of course, 10 times larger than this one. So it is in 1 megahertz. You can see it is very close to what we have here. That goes also for 1 gigahertz. 1 gigahertz is 111.5 microvolts RMS, of course, and that's what you see here. So, of course, if I go on 10 gigahertz, 1 terahertz, this will just increase. So you can already see from the plot that this is going without a limit to very large values. And that's why we have, of course, a situation where we know if you don't have a filtering, the noise will increase as the frequency band will increase. This is what we have here for the total RMS output noise voltage. And this is then in accordance to our calculations. So the simulation and the calculations are very close to each other. Not exactly, you can see that there's a very small difference, but it is very close to what we had. Now, finally is the signal to noise ratio here. The signal to noise ratio plot is shown here. You can see that the plot started very large at 1 millihertz. For this first circuit, it will decrease and then show some linear decrease in this log scale. Now, if I now look also to my formula where we have used this, and then also again get back to my table for the frequency bands and also the total RMS output noise voltage, and what we see is then these values. You can now check this. It is at 1 kilohertz. What this value here is 139.06 dBs, which is very close to what we have here. So that is really, really nice result. If I go to 10 kilohertz, I can see it is 129.06 dBs. Also very close to what we have here, 129. What you also see is, since this is a decrease of 10 dBs, this is also a decrease of 10 dBs when you increase your frequency 10 times. So this is also in agreement with our calculations. So if you move on, you will see the exact same results. If you go to 1 gigahertz, that's actually this value, 79.05 approximately, and I have 79 dB. So very close to what we have also in our calculations. So the simulations and calculations do confirm very well for the input noise spectral density, for the output noise spectral density, and also for the total RMS noise voltage, and also for the signal to noise ratio. These four elements we have calculated and also now simulated the values, and we have shown that this is indeed correct. We can also do that in the SPICE itself. So let's look at it in SPICE and see what we can do there and how we can generate these plots in a nice way. So let's now jump to the SPICE simulator. Now this is the simulation circuit in SPICE, specifically the TINA TI SPICE. I have the circuit here, so I have the 1 kilo ohm here and the 3 kilo ohm here. This is my measurement point, and this is the input voltage. It doesn't matter what the input voltage will be. You can have a unit step, you can have a square, you can have a sine or a cosine, it doesn't matter. Just an AC input voltage source in here, of course, ground this, and then you have the complete circuit. What we have is then analysis, and then go to the noise analysis, and then define a frequency region for this. So you can start at also at 1 kilohertz, it doesn't matter, but I just started at 1 millihertz, as I did also in the analysis before, and then end frequency is 1 gigahertz. This is actually a number of points to make it accurate. I found out that this is actually what you can get at max, so this is the most accurate number of points. And then we can then select here different plots. So I can have an output noise, that will be just of course the output noise spectral density, input noise spectral density, total noise, which will be just the total RMS noise voltage, and also the SNR, signal to noise ratio. So I will just plot them all. Let's run this. That's all actually. Very straightforward. Okay. That's the plot, and it will be generated now. You can see that this is not really clear at the moment, so I will make this larger. This is for the output noise. So I will make this clear by making lower limit 0 and upper limit 4 nanos, and I will have 5 spacing, so 1, 2, 3, 4, and then I have this. This is the frequency, and I can also make this go to 11 points, maybe 13, that will be fine. So that's the frequency, and this is then, if I now make this blue, can be better seen, this is my output noise spectral density for the frequency. So if I now go with the label, you can see it was this, you can see the 3.53 nanovolts per root hertz, of course, because if I move on, that will not change. Now, if I also look at the input noise voltage spectral density, again, this is not a really nice plot, so let me also do that 0 and a 5 nano. So 0 and 5 nanos for this. This is 0, this is 5 nano, and again, let's separate this in 6 pieces. This is what we have. This is then here also in 13 pieces, and I have this plot. This is then the input noise spectral density. And again, if I make this blue, so this is easier to see, then we have this one. If I now label this, you can see it is 4.7 nanovolts for this root hertz, of course, per root hertz, and that doesn't change. It's for all frequencies the same. So as we have calculated. Now, if I look at the total noise, you can see it is increasing. So if I make this again 13 steps, I have then the frequency here in the horizontal axis. This is then the total noise, RMS of course. And if I now look at some specific value, let's say 1 mega or 100 kilo, it doesn't matter, we will see 1.11 microvolts, which is then of course an RMS, and it's actually very close to what we have calculated. And again, if I move on to 100 mega, it will be 35.26 microvolts. Again, all in confirmation with our calculations. Now finally, I will look at the signal to noise ratio. This is this plot. Again, let's make this in 13 steps. And this is just the value of the signal to noise ratio in dBs, and this is the frequency where we have here. The frequency here is of course a little bit different because I really need to start at 1 milli, and then this will be fine. Then you can see the plot here, and if I now change this to maybe a little bit of pink color like this, this is then the signal noise ratio. And if I look at, for example, 1 kilohertz, you can see that this is the 139 dB approximately, and for different value make another label, for example make it 1 mega. You can see I changed my frequency actually from 1 kilo to 1 mega, which is then 1000 times larger, and this will go down by 30 dB. You can see this is changed. So for 1 megahertz I have a signal to noise ratio of 109 dB approximately. For 1 kilohertz I have 139 dB. So for each increase in my frequency in decades, so I have now between the 1 kilohertz and 1 megahertz, I have 1, 2, 3 decades increase. That will decrease my SNR by 30 dB. So you will decrease your SNR by 10 dB for each decade increase in the frequency. And this is also in confirmation with our calculation and analysis we have done. So that's what actually for example number 1, specifically for the noise analysis. And this is our first example where we see a passive circuit. We will continue also with different passive circuit like an RC circuit, and also use much complicated circuits using op-amps, and also single stage and multi-stage op-amp circuits. So keep in touch, and if you have any questions or comments, please let me know. And see you next time, and take care.